cross-n grid where each cell can have only three values. 0 represents an empty cell, 1 represents a fresh orange, and 2 represents a rotten orange. Now every minute, a fresh orange that is food directionally adjacent to a rotten orange becomes rotten, right? So it like spreads like this, okay, like this. So yeah, this example image is really good. Anyways, so return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. Okay, so first off, let's just like paraphrase it a bit. So like what they really want is we need to find out the maximum distance of an orange such that it is like it is at the maximum distance from any rotten orange that might be present at t equal to 0, right? So basically, like you want to find the farthest orange and the distance from the rotten orange that it is at, right? So like this one is like the farthest orange. So like the rot, I guess, it just propagates like this. So 1, 2, 3, 4. So like the output is 4. Now you might think is like this diagram itself reminds you of like the maximum height of a tree or something, right? So like you just need to find the maximum distance from one node to another, and of course what better way to do it apart from BFS, right? So we go for BFS right here. So what we are going to do is that we are going to simulate the rotting oranges uh, as the BFS layers they propagate, okay? And so like, and also let's just think of the termination conditions. So of course, one termination condition is like that all of the rotting and withering that has been that could be offered by this grid, it has already happened, and still there is a orange that is not being affected, which means that this orange will be an isolated orange, right? So then we return -1, and if there is no such orange, we basically return the number of minutes, which is the distance right here. Okay, so let's just code it up a bit. These are really easy to understand. These examples. So like you can see that here is an isolated orange right here, and and also like uh, there is no rotten there is no rotten orange in this one, and so the answer is basically 0, because like there are no fresh oranges at minute 0, so the answer is 0. Okay, so let's just try to code it up. So basically, first off, this is very simple, right? When you are given the grid, uh, and it's m cross n, so grid dot size will give you m, and grid 0 dot size, which is any element of the grid, that size will give you n. Okay, so because there are the number of rows and columns. Okay, so now what we do is we create a visited queue. Here we will like keep adding which oranges are rotten, and we will keep adding them as we propagate. Okay, so let's just and also uh, a useful idea, because we are finally going to need if there are any fresh orange in the board, and we might as well not again iterate over the entire grid, right, to find out the fresh oranges. So an interesting idea might be to like keep a track of which fresh oranges are getting rotten, and also it's like it's very easy to, because we need to at least go through the grid once, we might as well just keep a track of how many fresh oranges there are in the at the 0th time. So let's just take it. Okay, so so what we do is we iterate through the grid. This is just a normal like m cross n iteration traversal, and whenever the grid ij is 1, we just increase the term fresh. Okay, this is very simple. What we said, like keep adding the number of fresh oranges. I hope you got the reason why we are like keeping a track of numFresh in the first place because of this condition. If this is impossible, return -1, and we need to find out the remaining number, the number of fresh oranges at the end of our code run. Okay, so and this of course represents the initialization of the queue, the visited queue, right? The number of the all of the rotten oranges. We are going to like make a pair of them, and we are going to insert it in a vector of pair, or like queue of pair, right? Because this BFS. Okay, okay. So now because this might be a nice way to like account for examples like this. So if the number of fresh oranges is 0 at t equal to 0, might as well return 0. Okay, and this is a bit faster, right? Anyways, so what we do is we take a vector of integer, and this vector of vector they store the 4 cardinal directions that our routing can spread in. Okay, and why is this required? Because when you are going to propagate through each of the rotten oranges, you are going to move to the next wave by adding an offset of either one in this side, one on this side, or one in this side, or one in this side. So like, and you might as well like store it somewhere so that you do not have to hard code it all the time, right? This is very easy and intuitive, and we just do exactly that. We start with minutes equal to -1 because like if by any chance the number of fresh oranges do not stay 0 at the end of our code run, then we can easily return it. Anyways, so let's just continue. So uh, so because okay because we are trying to find out the number of minutes, so that means that the number of levels of the BFS traversal that we are uh, seeing right here is very important, because that number of levels is exactly correspondent to the number of minutes that we are going to have in this problem. Okay, so that's exactly what we do. We initialize the size of the visited array at every point whenever like it's necessary. Okay, so what this does is this keeps track of when the current number of oranges which are like in the current level it ends, so that that way we can like protect our traversal and keep track of how many levels we are going through. Okay, so this, whenever it ends, it means that a level of BFS has been completed. Level means like like BFS propagates like a wave, right? So like each of these waves I am calling it as a level. Okay, so anyways, this is very intuitive to understand. While size minus minus, you just like keep track of whatever you're doing, and then whenever the size is reducing, you like add a minute. Okay, like you can see it here. So whenever the size is completely going to 0, you add a minute. Anyway, so that's the entire point of while size minus minus. Okay, so let's just see what we do next. So basically, we have to move to the neighboring oranges, to the rotten orange, and that's exactly what we do. We like take the first element randomly, and then we just take the next x and next y that we are going to use, and this will exactly move us to the next neighbor. And because we are iterating over all 4 cardinal directions, this should theoretically move to all neighbors, and that's what happens. Okay, so now we of course some constraint checks. We do not want next x to be less than 0 or greater than equal to m, and similarly for next y. And for grid next x and next y, we want to make sure that it's 1, because like there is a 0 condition as well. So if it's 1, we just replace it by 2 because it's now rotten, and we reduce the number of fresh oranges because an orange is getting rotten, and we push it to visited array, and that means that basically our BFS is nearly done. Okay. Now what we do is that we pop the current element so that BFS can terminate, and then until visited is not empty, we just keep adding the minutes for every level of traversal of the BFS. So after this, basically what we have is either now stretch is 0, which means that we just return the minutes, or it's not, which means that there is an isolated component and hence we just return -1. As simple as that. Okay. So this is a very nice way to start BFS. Let's just see an allied problem to reinforce the understanding of this. Okay. So yeah. So let's just see an allied problem. Okay. Okay. So this is basically called a battleships and a board. This is the problem number 419 of LeetCode. Okay. So let's just check it out. Um, so basically it says that there is an M plus n matrix board where each cell is a battleship X or empty, and we have to return the number of battleships on the board. So, and it has been stated that at least one horizontal or vertical cell separates between the two battleships. This is very important. This means that you will not have something like you cannot have something like a cross here. Okay, because then that means that there is either a horizontal battleship like this and a vertical battleship like this, and so basically you will not see any L-shaped or irregular battleships. Okay, so you do not need to like worry about propagation to different directions. So let's just see what happens. And yeah, the battleships are all either row shaped or column shaped. Okay, 1 plus k or k plus 1, you can be anything. Okay, so let's just check the answer out. What I have written here. So we are not using the visited array. Okay, let's just remove that for sake of convenience. We are using q here instead. So anyways, so similarly m and n, new x, new y, answer, we just like initialize all those variables. Uh, similarly, this is like almost a ditto copied question or something. So like we also have a directions vector here. Now for every cell, we want to check if it's x, and then we want to check the neighbors. If the neighbor is also an x, we again want to check the neighbors, right? So this is like BFS, but we have to make sure that each component, like whenever the BFS is over, you like increment answer. Okay, so that's exactly what we do. We just so basically for every cell in the board, whenever the board piece is X, basically, so there's a battleship element right there. I push it to Q and increase answer because there's like if there's a single element, then it definitely means that there's a battleship right there. Now, until Q is empty, we do BFS in the exact same way as we did earlier. Okay, so this is the neighbor thing, right? And this is the constraint thing. And whenever it's x, we just push it to the q. Okay, so that means that whenever we are like starting the battleship element here, when we are on this cell, then by virtue of DFS, we keep on adding this and then this, and it just keeps adding, and you can keep pushing the pairs that are coming up. Okay, so yeah, so we have this exactly same kind of problem, and this does it. Okay, notice how whenever we are encountering the first element of the battleship, the entire battleship is being covered by the exact same process, and during the first encounter only we can update the answer, and then we just return the answer. It's very simple. So this is like a simpler version of the last problem. Okay. This is problem 419 of LeetCode. So yeah, that's it.